Okay, let's build some trees. So we will start by loading data first. This is the alignment file that we saved yesterday. So we'll use the mega format alignment file. Just open it. Now you see the data is already loaded. You can look at the alignment. Now we construct phylogeny by clicking on the phylogeny tab. We will first make a neighbor joining tree, but there are multiple options as I'll show you in my slides. So go and click on the neighbor joining tree construction. Click OK. We are not going to test for any phylogeny at this stage, and we will use the amino acid substitution type and beat distance as a method. We will let the rate among sites be uniform at this stage again. So the first tree, we are not going to change anything. Just click OK. And this is the first tree. So you have already built your neighbor joining tree based on the alignment that you had saved yesterday. Now let's have a look. So you see a bar at the bottom with a number. That actually is the meter for length of each branch that you see in the phylogeny. You can change the topology, at least how the tree is structured, how it looks. There's a traditional one that you're looking at. You can change it to radiation. You might have seen this in some manuscripts. For the limited amount of data that we have, there's no point looking at the radiation. It makes more sense if you have a lot of data in there. The other one is a circle one. Here you can have a circular plot. It also makes sense if you have a lot of data in there, not with the limited amount of data that we have. So we'll go back to traditional rectangular tree topology. Okay. Now, you can change the traditional from rectangular to straight. So it doesn't do anything else. It just changes the way lines are drawn. You can also draw curved lines, and sometimes they're just used to beautify your image, nothing else. Basically, it's conveying the same information. This is the cladogram, and this is the one that we are going to be using for now. You can change it. Yeah. So right now you see all the branch lenses are different. If you draw this cladogram, there you'll see that at every split, like gorilla and gibbon branches are the same length, and if you add it, then you'll see the other branches. Let's just stick to the traditional rectangular one. And now what we want to do that right now the tree is rooted at human, so we will select this root option and we will root it at gibbon. We know gibbon is the outgroup in our analysis, so we're going to root it at gibbon. And again, just by rooting at a different branch, nothing changes. The lengths are all same. It's just the topology looks slightly different, but in reality, it's just that you have removed the root from human and gone to gibbon. Now you see that the human branch is pretty long. It's even outside what you were looking before. We can go back to the cladogram. It will again look the same. And if we click back, then, so the human is the longest branch. And then this tree shows that its sister species is chimp, which is correct. And then their common ancestor sister species is gorilla. We can make it curved. It just doesn't look any better. Okay, and then the sister species of gorilla, not the sister species, it's rooted, the whole thing is rooted in the gibbon outer branch. Now we will make another phylogeny. This time we will use a maximum likelihood method. And just say yes. Okay, so now, again, we are not going to test the phylogeny at this stage. However, nor are we going to change the rate among sites. What we are going to do is see if what's the default option for the heuristic method of ML. We'll stick to that. We see what are the other options. We are not going to change it either. We are just going to stick to the default. But it's better to know what options are there. And then just go and see. You can do branch swap, but again, we are not going to do that. Just press OK. And now you have your maximum likelihood tree. And if you compare that with the other tree, you will see there is a difference. We will again root it. Let me place it so that you can compare stuff. Okay, so we will again root it on given branch. And now if you compare, you will see a difference. So now chimp and gorilla are on the same level, and the human is the sister species of the common ancestor of chimp and gorilla. And we know that is not the case, but that's the maximum likelihood tree that we are left with. Now let's make another tree. This time we will make use the maximum likelihood approach, but now we will do test for phylogeny. And the way we will do it is we will select bootstrap method, and it says 600, but we are just going to do 100 bootstraps, because the more bootstraps that you put in, the more time it will take to build the tree. Okay. And as you can see there, the replicate numbers are increasing. On top, there's this log likelihood score for each replicate. You are not concerned with that at this stage. We're just waiting for all the replicates to be constructed. So the moment this reaches 100, you'll see that the results are out. Voila. We get the original tree. If you look on chimp and gorilla, you already have a number. It's 24. I think it looks like 24. So basically, this is still the original tree. It looks same as what we had when we made the first maximum likelihood tree. Now we want to build the bootstrap consensus tree. So we click that option, we choose that option. So now you see this tree looks, the bootstrap consensus tree was pretty close to the actual tree that we know human, chimp, gorilla, and gibbon have. So that's one advantage when you do bootstrapping. Even if the data has some partial bias, just by bootstrapping, we can overcome that and see how many times we see a particular node being split. I will discuss this in detail a bit later. Now I want you to add branch lengths on all of these branches of the original tree. And when you choose that, this is what happens. Let's do that for the maximum likelihood tree that we built. And just to show you that both are the same tree, you will have exactly same branch lengths on both of these trees. And now let's also do it for the neighbor joining tree that we did. There the branch lengths are different because that was a different method altogether. Now we can save our trees as save PDF file. Go and save the image. Give it whatever name you like. Be aware that because you will be saving multiple trees, they should have unique names. Like this one, I'm going to call maximum likelihood tree 1. I should actually call it maximum likelihood tree 1 with my gene name. But anyways, you just go and save it, and it gets saved as a PDF file. Okay,